Can you hear us?
Francois, can you hear us?
Yes.
Okay.
All good?
Yeah, I think we can start.
All right, let's start then. Welcome to the last session of the day before the panel discussion. We'll have a few talks and we'll start with Daniel here. Go for it, Daniel.
Can you hear me? Okay. Okay, I am Daniel Andres. I'm a last year PhD student on Autonomous University in Madrid, and I'm going to give a talk about how to use deep learning models to infer mass maps from multi-view observation of SEC, X-ray, galaxy cluster members in galaxy clusters. Okay. Okay, why galaxy clusters? They are very interesting objects. Okay, they are the crossroad between astrophysics and cosmology. So in order to study them, there are giant laboratories in which there are different physical processes involved, like cooling, star formation, supernova feedback, AGN feedback. But they are also very important in cosmology because of their masses. They are the most massive objects in the universe. So to infer their masses and to calibrate their masses is of great importance to infer. So you know the masses of galaxy clusters as a function of redshift. You can actually infer cosmological parameters. So they are very important. Okay, the motivation of our work is that, well, it is based on our previous work. So in our previous work, we make inference of the mass in galaxy clusters, but the mass as a scalar, the total mass inside an overdensity. We want to generalize this approach to infer the 2D mass map, the 2D mass map, an image of the mass from mock observation galaxy clusters that I will describe later. As a matter of fact, the mass of galaxy clusters, you can see that this 2D mass map using wiki lensing. Wiki lensing will give you directly this mass map. But wiki lensing masses, so wiki lensing maps, are scarce in the universe. So we have tens of observations of wiki lensing, but if you observe galaxy clusters in stars, so the galaxy members or microwave, you have surveys of thousands of observations of galaxy clusters. So this project will make this observation more available and easier in regards that you can have mass maps from other traces. Well, this is what I told you before. This is I will describe this very briefly. You can observe galaxy clusters through the SEC effect. The SEC effect is the Compton scattering. So in the galaxy clusters, you have gas. There is the CMB. So in the gas in the galaxy clusters, they heat a little bit the CMB, so you can observe the gas of the galaxy clusters using this effect. This is a very beautiful image. You can also observe the galaxy clusters in the X-ray because of the break radiation of the electrons of the gas, and you can see the diffuse emission is the X-ray emission, and you also see all the galaxies. So with this beautiful picture of the coma clusters, you can see how can you observe a galaxy clusters using multi-wavelength observation. Okay, this is as a motivation. This is our final objective. So what we do in all our work is to train the machine learning models with cosmological simulations. You see here. Okay, you see here we can train with a cosmological simulation. So we simulate the universe, we simulate this signal that I told you before, the SX signal, and then we introduce instrumental noise such that it is the same as in the real survey. This is the Planck quantum wave map. So you can see statistically they're very similar. We train on this data set to predict the masses of this object. And well, this is what we did in our previous work. Well, after the motivation, I'm going to talk about the outline of this project. I will give a very brief description about the 300 project. Then I will talk about the mock data set that we have used, the simulated data set. And then I will discuss our results. Okay, this is the 300 project. I think from this image, everything is clear. But inside this project, we have a machine learning group, which is, we have lots of collaborators. And in case this image is not enough for describing the project, I can tell you here. Okay, the machine learning project is a set of cosmological simulations. They are based on the zooming technique. As you can see here, we have a dark matter-only, n-barrier-only simulation, gravity-only simulation, and we can perform the simulation in a very big box, 1 gigaparsec of box size. And then, but we cannot do, what we cannot do is to fully simulate the whole box with full hydrodynamics. What we do is, from this big box, we resimulate from the same initial condition hydrodynamics on the most massive regions, which is 15 megaparsec. So at the end, we have very massive galaxy clusters. So at the end, we have, by doing this zooming technique, we have very massive galaxy clusters. So these simulations are tuned for studying galaxy clusters with a particle resolution which is very well below the mass of the galaxy cluster. So they are very good simulation for studying galaxy clusters, and they're very well resolved. We have performed the simulation using 3 different versions of the, so the same simulation is resimulated with different variant physics, well, the different simulation codes, Gadget Music, Gizmo, and Gadget X. We also provide mock observations for different instruments, such as the XMN Newton collaboration. Okay, now I'm going to talk about the deep learning models to infer mass maps. And first, the mock data. Well, as I told you, as a first approach, we want to generate idealized or theoretical data set of simulated observations. In this case, the data set is based on Compton-wide parameters that I just saw an image before, volumetric X-ray surface brightness, you also saw an image before, and for the stars, we use the star density maps as the proof of how the galaxies are located in the sky. And the objective is to infer, of course, the mass density of the galaxy cluster. Our data set, the most important feature of a data set is from the 300 simulation, we can have very massive objects of galaxy clusters. I mean, the simulation provides these objects, and we have sampled the objects to follow an uniform distribution in mass, so that when training the model, the fact of having more objects at a certain mass bin is not biased in the results. From our simulation, we have almost 5,000 different halos, using 29 line of sight projections. We end up with a lot of images, almost 150,000 images to train our deep learning models. Our images are sampled to cover R200. Twice R200 is 80 pixels, and they are Gaussian smooth with a very small bin. This is how our data set looks like. So at the end, our problem is stated as follows. We have mock observation or idealized observation of galaxy clusters of the microwave, X-ray, and the stars. And the inference problem is to get the mass density, which would be similar to doing weak lensing, but only from this information that is more available in service. Okay, going to talk about the model that we have chosen. You go to the literature, the model for doing this is based on the pix-to-pix translation. You go to this, it's based on conditional GANs. And as you see, these models can give you very detailed, these GANs can give you very detailed descriptions on how a human face is, they can solve a lot of problems with the same loss function, which is an adversarial loss function. So they can be applied to almost everything. We wanted to apply these models into our work. If you go to the literature in the same work, they use for the generator, they use the unit architecture. The unit architecture is based on the encoder-decoder, but with a skip connection. You probably know that. So I'm going to skip. The most important feature about our model is how can we handle this multi-view input. So we have this multi-view input. How can we handle? What we did is to design one encoder per input view. So we have a SEC, X-ray, stars. We have 3 encoders. All these views are flattened to a latent vector. And in the latent space, what we do is to concatenate this information, and then we have one decoder to get the output. We have trained the model with the L1 loss function, and we have also tried a conditional GAN coupled to this L1 loss function. And luckily, the L1 loss function is the best for this task. So we don't need the generative adversarial network for this. And this algorithm with 10 layers have 7 million parameters. Okay. Going to talk about the predictions. The predictions that you can see from this map, the SEC map, so we can have one model, a single view model. We end up with this prediction. This is the ground truth. You can see from the residuals, that is the difference from this and this. You see, you find all the substructures that, of course, you see the original map, they are missing. So at the end, you use gas tracers, XC or X-ray, you end up with a continuous field with all these points that are missing. So at the end, because this high frequency information, spatial frequency information, is not present in the input views. So it cannot be the model. Doesn't matter how powerful the model is, you will not infer that. From stars, what you do is to take the small frequency information, and at the end you see that the prediction is very good. So this is the original map, this is the prediction. At first sight, it's very difficult to tell the difference, and the residuals are more continuous. They are not this all spatial, smallest, this is not full of these high spatial frequencies. And also when you use the multi-output model, you have a better prediction, and you have that the residuals are almost zero, a very low error. So that this map is quantitatively very similar to that. And this leads us to the most difficult part of the analysis. So you have a very good model, but how you can test that the generative maps are precise. And for that, we have designed 4 tests: pixel-wise statistics, mass profiles, power spectra, and a test based on a metric that is the maximum mean discrepancy. For the sake of brevity, I'm going to discuss only this. You see, these are the mass profiles. The mass profiles are the mass integrated over a circular region. This is called the bias. The bias is the difference between this is the predicted mass profile. This is the true mass profile divided by the true mass profile. So this is like a percentage error of your estimation. These are the single view model. So you have only one input, you get this result. 0 would mean perfect result, and this is the scatter. You can see for low mass clusters, the scatter is almost 20%. For massive clusters, the scatter is 5%. But when you go to the multi-view models that I described before, the scatter is reduced a lot, so drastically, like almost 1/2. So this is the importance of consider multi-view, so multi-wavelength analysis. So consider different surveys, different instruments, and combining using machine learning, because machine learning provides a very easy way of combining these multi-frequency observations. Thank you very much. This is the take-home message. The only important thing here is that for all these projects, cosmological simulations are invaluable. So you need a lot of data for training, you need label data, and cosmological simulations, I think they are, well, it is a limitation of the model because you have to simulate your data. It's not the real universe, but they are very useful to get those label data that are very important. Thank you very much.
Thanks a lot for the very nice talk. Do we have a question here in Paris? And the next speaker should come down. Yes.
It's a very quick question. Technical.
Okay.
Did I read correctly that you have 5,000 halos of virial mass above 13.5?
So you mean the data set? No, we have, at the end, you have a cosmological simulation populated with halos. We have 5 different halos. And then for each halo, we take 29 line-of-sight projections.
Okay. So it's not 5,000 clusters in the simulation. That's what I understood.
No, there are. So for this case, we took 2 simulations. One is the Gizmo Simba simulation, a different code, and GadgetX simulation. Each of them has like 2,000 and something different halos. So if we combine, there are 5,000 different halos.
With virial mass above 13.5, so 5,000 simulated clusters.
5,000 simulated clusters. And this is the statistics. This is the, you can, the slides. Thank you. This is the, you can see the statistics. This is the different halos. So this simulation is tuned for analyzing galaxy cluster halos using the zooming technique. This is why this simulation is very important for galaxy clusters. Because of the statistic of massive halos. Yeah.
Thanks.
Do we have a question on Slack? And any question in New York?
Did you compare with not machine learning? I mean, you can estimate the mass just using profiles and so on from these data. So it'd be interesting to know how much the machine learning is picking up that isn't the obvious things.
Well, I mean, this approach has only been, well, the fact of computing the mass density map has only been done with machine learning. There are no other way of sorry. there's no other way of inferring well, statistically you can infer the mass density from this. And we have done, you mean a comparison between classical models and machine learning? In this work, we have done that. But in this work, we do not infer the full mass map profile. We infer only the mass of the galaxy cluster inside. And there are a lot of classical approaches. The classical approaches, I can explain it to you in 1 second. So they take this signal. They take this signal. They integrate this signal in this aperture. And this integration is a proxy of the mass. So they compute the mass from this integration, and we have compared how machine learning works from that. Machine learning is not a spherical model. It works much better than this, but it depends on the physics implemented on your simulation. So the message from this is that machine learning is not biased because of the symmetry of your gas distribution, so you can work with very complicated symmetry, but it is biased on the physics that is implemented on the simulation. And for that, you have to use domain adaptation techniques or simulate different cosmological simulation with different physics.
Thank you very much. I think in the interest of time, we'll switch. Yeah, we have plenty of time at dinner to chat more about these questions. So let's thank Daniel again. Okay.